Now we start, okay? So, hello everyone. Good morning or good afternoon. Welcome to the AFOMP monthly webinar. So, AFOMP is celebrating its 20th anniversary this year. In order to promote the education and the training of the medical physicists during this pandemic, the Education and the Training Committee of AFOMP has scheduled a monthly webinar from June to December 2020 and offer the continuous progress education points, CPD points, with joint endorsement from Australian colleagues of physical scientists and engineering in medicine. So we have topics covered from various topics in the medical physics. So today's topic speaker will be the Professor Golman Abu Zakari, and moderated by the Dr. Kanchan Adhikari. So I will give a brief introduction of Dr. Adhikari, then I will pass the speak to Dr. Adhikari. So I will introduce him first. Dr. Kanchan Adhikari is the Associate Professor of Medical Physics in National Academy of Medical Science, Hospital, Kasmudu, Nepal, Science, 1998. Dr. Adhikari has been involved in academic activities in anti-diagnostic radiology, MD radiotherapy, and Bachelor of Science in Medical Imaging Technology. He has also been involved in supervising and guiding postgraduate students in the field of radiation medicine. He has completed different project works in radiation protection, inventory of the radiation source for the government of Nepal. Dr. Adhikari has designed various national projects for IAEA and also working as a national project counterpart for different IAEA technical cooperation projects. Dr. Adhikari had presented papers at various forums and published papers in different journals. Dr. Adhikari is also affiliated to AFOMP Award and Honored Committee, IPCB Committee, Edited Board Radiation Regular Journal, General Secretary, Nepalese Association of Medical Physics, and Secretary of Nuclear Science of Nepal. So now, welcome Dr. Adhikari and Dr. Zakari.
Thank you.
So, Dr. now it's turn to you.
So, good morning, good afternoon, good evening, everyone, and welcome to the AFOMP webinar. So, I would like, which is organized by Asia Oceania Organization for Medical Physics. So, I am Kanchan Adhikari. I have already introduced by Dr. Zeen. So, I'll be your moderator for today. So, our talk program will be approximately around 60 minutes. During the presentation, if you have any questions, queries, or anything, I would like to request you to ask anytime. So we'll try to accommodate all the questions with a priority basis. So today's talk is dosimetry of small photon radiation field, comparison of IAEA TRS 483 and the German DIN 6809 protocols, which is going to be presented by Professor Ghulam Abu Zakaria. So he is the pioneer medical physics. So he has been involved in many activities in the Asia and in Germany. So before, next slide. Just a minute. The key points of the today's lecture is characterization of small radiation field. So you are going to learn more on detector related for small field condition, reference dosimetry according to the IAEA TRS 483, which was published in 2017. So you guys are also going to learn on reference dosimetry according to the TEEN protocol 6809, which was published in 2018, relative dosimetry, suitable dosimeters, output factors, and comparison. He's going to compare it TEEN 6809 and TRS 6483 protocols, experimental data, materials, and methodology. So after that, after the key points of the today's lecture, I would like to give a brief description about the Professor Zakaria. So he has done his postgraduate physics with specialization in medical physics at the University of Halle-Wittenberg in 1978. And Dr. Zakaria completed his PhD in medical physics from University of Heidelberg. So his tenure as a residency as a PhD candidate was from 1981 to 1986. So he has served as a vice chairman of the DGMP Working Group for Medical Physics in Developing Countries of the German Society for Medical Physics, Germany, from 1993 to 2001. Similarly, he has served as a chairman and chief medical physicist at the Department of Medical Radiation Physics, Gummerbech Hospital, Academic Teaching, University of Cologne, Germany, from 1987 to 2019. So he has been affiliated to many organizations. So right now, he is the chairman of the DGMP Working Group of Medical Physics in Developing Countries of the German Society for Medical Physics. Similarly, he is a founder, partner, and professor and coordinator of the Department of Medical Physics and Biomedical Engineering at Gono Vishwavidyalaya. It's situated in Sabar, Dhaka, in Bangladesh. He has been also served as a chairman. He's currently a chairman and founder member of the South Asian Center for Medical Physics and Cancer Research, vice chairman of the Accreditation Committee of the International Organization for Medical Physics, and he has supervised more than 150 bachelor's, master's, and PhD thesis of the PhD students, and he has more than 100 scientific papers, including scientific conferences, proceedings, and proceedings. So as a he has awarded by various honors and awarded. So main award which I would like to highlight the only two because of the single frame. The Oncology Club SARC Federation of Oncologists honored with highly prestigious award outstanding personalities of the decade of 2000 to 2010 for the unique contribution to establish medical physics in Bangladesh. So he got this award in 2009. Similarly, he was an awardee of the Global Radiation Oncology Distinguished Leader Award 2019 by the Global Health Catalyst of the Harvard Medical School. So this is the brief introduction of the Professor Zakaria. So I would like to hand over this forum to Professor Zakaria for your talk. So thank you. Now the floor is yours.
So thank you very much, Professor Kanchan Adhikari. First of all, I thank the AFOMP authority, especially its president, Professor Arun Chokle, and his staff, to invite me to give this opportunity to talk about a special topic to this prestigious conference. And they have supported me so nicely, so they support me everything, even good technical support. So we have now a good contact. I hope everybody can hear me around the globe. And I introduce this topic, small field dosimetry. So I will start with my topic. It takes a little bit time, I do not know. So So thank you once again. My topic is dosimetry of small field radiation fields. I will compare both protocols, the international protocol IAEA TRS 483. You know, everybody, this is an international protocol. It is a very nice protocol. And of course, a German protocol in DIN 68098. It is a protocol new for you, but I try to give a small description so you can understand the philosophy of this protocol. So this is the contents. It was already.
Excuse me, the slideshow, you are not yet shared. So it's not visible on the screen, yeah.
It's not in the screen?
Yeah, not on the screen. Please share it.
Oh, sorry.
So you have to share from the green down, yeah. So now.
Oh, I talked the. So now I can start, yes? So
you go to the slideshow.
Yes. So once again, yes.
Exactly.
I have already given you the name of the topics. I go forward. So this is the contents of my topic. It is actually 3 parts. First of all, I give all the details of the problem and definition of small field dosimetry. And the second part, the physical background, formalism, and all associated terms for the both dosimetry. And the third part, I will compare both protocols with our own experiences and experimental data. So, so everybody knows radiotherapy is an essential that we should determine the dose very accurately, and which is also important. The key points is consistent reference dosimetry, which is traceable to primary standard. This is very important. And, and at the same time, the dosimetrical error in small field dosimetry is higher than the conventional dosimetry. The conventional dosimetry is designed for reference field size 10 by 10 and 10 centimeter distance. And it is a calibration coefficient with standard primary laboratory. Some people used this protocol for small field dosimetry. Therefore, massive mistakes, and in some cases, it result accident. Here, but in our time, there are a rapid increase of new design radiotherapy machines, especially, you know, the chemotherapy and CyberKnife, and many new treatment modalities like IMRT, VMAT, SRS, SBRT, which use mini or micro MLC created fields less than 1 by 1 centimeter. And the dosimetry of this small field is a challenging work. And currently protocol, you know, IAEA 398, AAPM, TG51, and DIN 68002. These are few of many protocols in the world, which is designed based on the ionization chamber at field 10 by 10. And in this protocol, medical fish is used all over the world, but no advice is given for the procedures of small field sizes. Therefore, experts all over the world is trying to develop new types of protocol. Today we have 3 protocols is existing. One is IPM report 103, was established 2010. And another protocol, you know already, IAEA TRS 483, and the DIN protocol 68098. So the characteristics of small radiation fields, how can we define small radiation fields? The following condition, when fulfilled a field, then it is called a small field. The first is beam related conditions, and second, a detector related condition. On what is a beam related condition? If the focus is partially hidden by the collimators, it is called source occultation. You see in the photos in the middle, you cannot see the whole focus here from through the collimator. That's why it's this source is occultation, and it should be fulfilled by a field which can be called a small field dosimetry. And secondly, the lateral electron equilibrium is not given in this central, is here. This field when is small, the radiation outside cannot come and make a equilibrium in this chamber. So it is a equilibrium condition. And last but not least, the size of the detectors. You saw the size of detectors compared to the dimension of the field. When the size of computer is equal, or all the three result is overlapping between the penumbra and the detector volume. So I go quick, the source circulation, you see two photos left and right. Here is a large field, and in large field you have normal condition, the full output you can measure here, and no occultation. And the small field dosimetry you see here, this is the dropout. Here is drop dose, and the penumbra is overlapping. So you have some more problem related to small field dosimetry. So here again, source occultation effect. You see when you have a large field, then the actual field settings through the collimator is equal to the MWHM of the resulting dose profile. That means when you measure the field size with the profile and the setting to the collimator, they are the same. But in a small field is not. You see the setting collimator is less than the measured field size through the dose profile. That's why we should always measure the dose profile to use some lookup table in the protocol. Here is the third point is the lateral charged particle equilibrium. There is two photos in left and right. You see here is a large field. You have an equilibrium condition inside the chamber, but in the right side there is no condition of equilibrium, because the incoming particles is less than the outgoing particles. So this is a very nice slide, and here you can have some relation between the radius of lateral charge particle equilibrium. You see, you can calculate this radius from your quality index, and for different energy, we have different radius. What is important in these slides, you can see how you select your detector for given fields. And this is the relation, the focus, the minimum field size is equal to 2 times the radius plus the diameter of these detectors. So when you know the detector diameter, you can also define such type field which allow you a lateral charge particle equilibrium. Here is detector related small field conditions. You know there is many perturbation factor in detectors which can be corrected in the protocol so that we have a precise dose. In the right side, I have given some photos. You see in every photo in left side is a schematic diagram, and right side is a photo through X-ray. Before you use different types of detector, you should first make photos through X-ray, because you want to know inside the detectors where there is a mistake or some disabilities or some defect is there. And this is very important for a small field dosimetry. So I suggest every medical physicist before started their dosimetry small field, they should see the internal life of every detectors. Otherwise, you make mistakes in the dosimetry. So there is a relation is given by Kabachi. This is a very good relation where you can calculate the volume averaging correction factors. Yeah, this is actually from the measurement. You see from the measurement of the beam profile, and here actual dimension of the cavity. In this protocol, IA protocol, you find a very good explanation of this formula. Even they have give some example how you calculate with this formula. I think it is also very good for every medical physicist to know the mathematical procedure to learn these procedures. In the next slide, the Kabachi given some example. Here you see different types of field, and here is the ionization cavity length, and here is the underestimate. For example, when you have 2 centimeter diameter field, and you have a ionizing cavity length is 0.3, then you underestimate 0.5% dose. When the field size is smaller, then the underestimate is also larger. So here, once again, the volume averaging factor, the left side, you see a dimension of a detectors and different types of distribution according to the fields here. When the small field, then you have more mistake, more volume averaging, and when the field is larger than the compared to the, then you have less. And it is shown on the right pictures in one dimensional. So once again, the volume averaging, when you see very tiny detectors like film or diode, then you have see there is another distribution here in green than in the ion chamber. They have some mistake. Here is a wider half penumbra on less dose in the slope. This is same here. You can see there is a difference, and every medical physicist should know when they select the chamber, the volume averaging is an important, and it can be corrected. The value from each volume averaging is given in this protocol. So here is another important aspect. You see the displacement. When you have a, for example, a square field 5 millimeter, and you have some displacement measurement 1 millimeter, then you have a mistake still 3%. So the placement of dosimeter and its orientation is very, very important, and you should exercise so that you can place the dosimeter in right position where you want to measure. So here is another energy versus response. This is also very important. You see here different materials stopping power as well as energy absorption coefficient. You see for the silicon and water, there is in small energy, there is 8% more than the other energies, and which should be considered some detectors which is made of silicon in case of diode detector. Here is another important, it is done by the team of Dr. Scott, and they have done some very excellent experiment so they can show the detector density effect. What actually the conclusion, an ideal small field relative dosimeter should have small active volume and water-like density. It does not depends on depends on the composition. It depends only the density. So the density correction also needed. So this is another detector response versus field size. You know, this is actually important to calculate or determine the output factor. So which chamber you select for output factor? Yes, some detectors has over response in the higher field. Other detector is under response is lower field. So you should select a suitable dosimeter, or you combine different dosimeter, and through the daisy chaining method, you can have the values in whole fields. So this is the first part of my lectures. I am now going to give you the formalism of these both protocols. So everybody knows this formula and these procedures everywhere you find in literatures, especially in this protocol from IPM. You need actually this protocol from IAEA. It is sufficient for your hospital work. Everything is given there. The procedures is very simple, and all the values you needed is given in chart or in table. But this other one for the English IPM, I think it is also very nice to read. When you have a good idea about small dosimetry, you should have both protocols, because the English protocol, there is very background and many physics inside. So you understand why you need such types of correction factor and such type formalism. So I think both are very important for a hospital of radiotherapy. You see in the left side, the formalism of reference dosimetry. On right side is the relative dosimetry. And it is special machines, and they have special procedures. What is important, you should understand this abbreviation. What does it mean? MSR for F and Q. Actually, it is not so difficult, because you know everything from the TRS 398. But here, because the field is not 10 by 10, so they should have another formalism, and all the data you have from 398 should be transformed for the spatial field sizes, and such types of terms is needed, which correct from one protocol to another protocol, from one values to another values. So here I just give you once again the same formalism, and you see here is actually different terms. And in the protocol, in the first, I think at the beginning, they are explained very well. You should learn very good, for example, F small, that means field for small non-reference field. FMRS, machine specific relative fields, like this, okay. So here is a new design radiotherapy machine. That's why the machine specific reference field, you see here different field, they have the maximum field is not 10 by 10. This is our problem, and that's have this protocol. Here I will show you three formalism. This is the first. You can calculate the dose for the MRS field when you know the readings of MRS field, and there is a calibration coefficient for MRS field. Then this is the more simple way to calculate the dose, but it is not easy, or we have no data for this in MRS, because the primary lab, they have not such types of machines, so they cannot determine these values. So the second one, that's why important. This is actually chamber calibration for conventional reference field with a generic quality correction. That means you calculate the dose in these machines, but take the values of calibration coefficient for conventional field, what you know from 398, and you just correct it through these factors. And this is called, is a factor to correct the difference between the response of the ionization chamber from normal field to the machine specific field. And there is another possibility here when there is without generic beam quality correction factor. So this is actually the formalism, and this is the factor. You cannot find this factor in the protocol. So this is more or less 1. So you can put the factor is 1. So the dosimetry equipments, it is an important which chamber you select for the dosimetry for which field. Yeah, so in the TRS, TRS 483, they defined the to measure the machine specific field MRS, two types of field, 6 by 6 and less than more than 6 by 6 and less than 6 by 6. So there is two table, and you see here the next. These are the characteristic of ionization chamber suitable for reference dosimetry of MRS field greater than 6 by 6. That means it is actually conventional linear accelerator. So you know all this here, the rigid chamber and so on. You can use this chamber because the field is larger, and to measure the dose with such types of chamber, you have an equilibrium in the central position. That's why it is the normal way. And you see here the next table, when the field is less than 6 by 6, you select one of this chamber here. Yeah, you know the very important chamber is the pinpoint chamber. But in this dosimetry, you should select any ionization chamber. And these are the values is given here. Yeah, you see here the volume is very, very tiny because you want to measure the small field. Here is the determination of beam quality index. Everybody knows how determined the Q, or in actually TPR 2010 from the 10 by 10 field. You know everybody. This is actually here. But how we should transfer the for the small field to this value? How can we do that? This S is actually the equivalent square field of the MRS field. That means in MRS field 10 by 6 maybe, you can first calculate the equivalent quadratic field and then go to this relation where you have the measured value for small field and calculate it in TPR 2010 in 10 by 10 fields, and this can be used to have the values of correction. So here's the correction factors. Here you see the correction factor for different types of chamber. When here is actually the TPR, and here is cyberknife and tomography. So you can use such types of protocol and put in the formula, and you have the dosimetry. So I go to the protocol of German protocol. It is a little bit different, but we have shown they give the same result. This is the basic DIN norm from Germany, 68002. It just like equivalent to TRS 398. But the German, they have some special measurement places and some special things. So you have little bit other correct factor than TRS 309. You know from TG53, when somebody use TG53, they have some little bit different procedures and little bit different correction factor, but it gives at last the same results. So the German, they have this protocol, and this is actually the dose. The formula, you know everybody, except some correction factor, this is special. And when this condition 10 by 10 field in 10 centimeter depth, when you actually change it, maybe the depth or a field size, then you correct with a special terms. And this is for non-equilibrium field, and this can be calculated by Monte Carlo. This is actually the normal practice. But what for the small field, this practice does not function. So there is a special approach for the German in DIN 6809. You see, there is a schematic diagram. You know everybody up to here. And this is actually for high stable ionization chamber, semi-flexi chamber. You can do all here. But actually it is started here, the small field dosimetry. They have selected 4 by 4 centimeter field. This is a calibration field. This is actually the philosophy of this German protocol. They have selected a field 4 by 4, where you have a cross calibration with your normal chamber with all small field chamber. That means you have a chamber from the large field and the same chamber for a small field like diode, diamond, or pinpoint chamber, and put in the position, and there is a cross calibration. When there is a cross calibration, you have a calibration factor. You determine in your hospital, in your department, the calibration factor. When you have the calibration factor, then you have the dose of the small field where you have the readings and the calibration factor, what you are determined through the cross calibration and put it here. And there is another value, it is called correction factor, accounting for variation of detector response when changing in the field size of 4 to 4 to smaller field, just like the correction factor from IAEA. And when you have this, you can collect it. So this is the procedures of German philosophy. You see in German, DIN norm, they suggest any dosimeter, small dosimeter like diode or diamond or pinpoint chamber, you can use it as reference dosimeter. It is just a difference from the IAEA protocol. IAEA protocol only ionization chamber, but in German protocol, you can use any small tiny chamber when you calibrated it in your hospital. So this is a relative dosimetry. You know, this relative, the output factor is defined by the readings of the standard field, or reading of the different field, and then the standard field. In the case, you know, every readings of different field and then 10 by 10. In this case, every small field and not 10 by 10 because it is not existing in the special machine. So you have the machine specific field and you divide it. Only the division of ratio of readings is not enough. You should have a corrected factor here. You should have a factor which can be determined from the measurement or Monte Carlo. And this is called the ratio of detector readings is not equal to the field output factor. It needs output correction factor. This is actually important. Yes, and this is fine for every chamber, for every quality in the protocol. So you put it here. So relative dosimetry, we have another types of detectors. It is given in the protocol. You can select this, and this detector should be you know, the small ER field ionization chamber, radiochromic film, unshielded diode, diamond, liquid air chamber, and organic scintillation. These all chamber you can use for the relative dosimetry. What is important, how you select. Here is one thing I have written. An example could be the combination of detectors with correction factor above or below 1. So maybe you select 2 or 3 chambers and you take the average value. It is actually defined, but in our case, we have seen we use only 1 chamber in diamond. I will explain you. This is also give a very good correct value in the relative dosimetry. So I will give you the output factors. How can you determine the output factors? Some hints here: relative dosimetry, free choice of detector, large field sizes, not energy dependence. You see, when you use the silicon detector, I told you earlier, because of some small energies, less energies, you have some over response. But when you use the ion chamber, you have here, you see here, under response. So you should correct it when you determine the output factor. Here, such type of correction factor you find in this protocol. And for every chamber, I have given here TRS 483, the figures 25 to 31 and pages in there. You can find all chamber, the value, and you put your dosimetry. When you want to measure the deep dose curve, you see some here suggestion, relative measurement, free choice of detector, beam inclination, very important in small field. It should be the right beam inclination, effective dose of measurement, effective location of the detector should be well known and adjustable. And the large field size, not energy dependent. For a small field size, not the size of the detector. And finally, observe polarity and saturation behavior. And here the profile measurement is also important. Such types of recommendation, free choice of dosimeter, reference chamber should be used for balance and control the stability of the linear accelerator. It is done for the all measurement you have done every day. For large field sizes, not energy and dependence. For small field sizes, not volume and density effect. As I explained earlier, the density effect is should control. High density compared to water results in steep penumbra areas. You know why the steep penumbra areas when you use some detectors with high density is existing. So now from experiment data where we compare both protocols from our measurement. It was done our students, master students and other students, and we'll show in very concrete what result we have found. And this is the point. We have the reference dosimetry, output factors, and some relative measurements. You see here the left side, the DIN norm, and the right side, the procedures. Yeah, in DIN norm, you see 3 steps, but IA is 2 steps to determine the reference doses. I have explained already how you determine such factors. When you have some protocol, you can understand very well how it's functioning. So from the materials, we use our vital beam linear accelerator for 2 energies, 6 and 15. And we have taken 4 detectors. This is the normal detectors, then 1 pinpoint and diode and micro diamond. And of course the Unidose, you know, and the Phantom used software and OmniPro. All medical physicists know in the hospitals in their measurement instrument. Here is the experiment. You see the 4 dosimeter, 4 chambers detector. Here is the linear accelerator and all the things is given here. Water Phantom. So you see, once again, I give the characteristics of these 4 detectors. These detectors, you know it has the calibration factor. So through the cross calibration, we have determined the calibration factor for these chambers. And here is the volume of the chamber. You see is a very, very tiny chamber, is a micro diamond detectors. And this is also small. Pinpoint is not so small. And this is the normal chamber. You see in which voltage you need it. And it is actually the reference point of measurement. This should be very, very accurately placement is needed. And here you see the effective point of measurement, but last but not least, scan direction. Yeah, in which chamber use, there is a scan direction. When you use the pinpoint, the chamber should be in vertical. Here is vertical. And this is sometimes very difficult. The chamber, they have some marking. Where can you find the effective point? But in pinpoint chamber, we have no marking. So through these values, you should put right position. Here, actually, the comparison in different protocol, you see in German protocol, special 4x4 fields is the reference field size. In IA 10 by 10, and all the factors more or less the same. And what you see here, the small field specific correction factor in German, this is this factor. And in IA is this factor. Actually, this factor is taken also the German from some Monte Carlo calculation and of course from authors given. So the factors, many factors is similar. I think the IAEA, they determined the more current values of this factor. So here we have taken for this 3 chamber, yes, diamond, diode, and pinpoint chamber. We selected from the both correction factor from both protocol and put it here so that you can understand better what is the values for this protocol. Here is from DIN protocol values. Here is more or less the same, and then we have determined according to the procedures, the reference dosimetry for 6 MeV. You see the values for both protocol, uncertainty, the protocol shows no difference within the uncertainties. Yes, both protocol give the same values for diamond, diode, and pinpoint chamber. And we have drawn here. And another things you see here, DIN protocol, the systemic measurement uncertainty in 2%. So in the 2% is the systematic uncertainties. Also in IA at 1,5, and the deviation stand in this range. Here we have determined the total scatter factor in left side from DIN protocol and right side from IA protocol. And this is the deviation between the different dosimeter. You see here deviation little bit more, but in IA protocol exact all the 3 chamber has the same output factors. So the both protocol is similar and give the similar results. And I will show you here relative measurements from profile for 6 MeV. And you see for the field when is higher, larger, all the 3 chamber show is the same result, but for the field is when very small, you see some deviation. Yes, this is actually because of volume effect of pinpoint chamber. And again, it's 15 MeV. We can also measure, here is the difference a little bit more, because the 15 MeV, the beam modulation is not so good at a small energy like 6 MeV. And we have also given some values in relative dosimetry. You see for 6 MeV curve is the same when the field is small, some deviation, when larger field is no deviation. We have measured from 10 by 10 to 0.5 by 5. And here, once again, for the differentiation, we put it here. So this is important, you know, the left side, this is, you can find this photo in the protocol, TRS 483. The left side is 18 MeV and 6 MeV in the right side. You see here the modulation is better because in higher energy, the radiation, it is actually a photo is in the multiple, it is a photo which is the transmission is here is where, but in 6 MeV transmission less. That's why the modulation is better. That's why it is advised for the small field dosimetry, 6 MeV, 6 MeV is needed. And in the both protocol, you cannot find the different correction factor for 18 MeV because these are not recommended. So 6 MeV up to 10 MeV, you can find the correction factor. So I think time is also 45 minutes. Yes, summary, I give you some hints here. The TRS 483 advises to apply this 2-step approach. The DIN 6809 has 3-step approach. Standard dosimetry at the MRS or reference field traceable to primary laboratory. Relative dosimetry down to clinical field using suitable dosimeters. Required field output correction factors are made available in TRS 483 and DIN 68098 for a variety of ionization chamber and machine, a variety of detectors and their response characteristics suitable for relative dosimetry are described. Here field size dependency and energy dependencies have been demonstrated. A significant volume effect of pinpoint chamber has been demonstrated in small fields. The diode detector greatly overestimates the dose in large field. This effect can be seen more clearly at higher energies than at lower energies. And this is the conclusion. Dosimetry is a small field poses great challenge for medical physics. Position accuracy is very important. The volume characteristic should be excluded as much as possible. IA correction factor must be determined exclusively through extensive measurement or only by simulation with Monte Carlo calculation. Yeah, here is the research field where extensive research is going on. The calibration factor for high resolution detector should be determined and specified by the manufacturer for DIN. Recommendation by the manufacturer for specific detector diode need to be used as standard, because in DIN protocol, they do not give any calibration factor for any chamber for small field dosimetry. So you should determine in the hospital, then it needed very exact determination. So sometimes in the hospital, we have less time. So it is advisable that the manufacturer should give us a correct calibration factor like the large chamber. So here is actually my references, which is used for this work. And thank you for the invitation. And I hope these lectures give you a small introduction in the small field dosimetry, as well as a introduction of the German protocol, DIN 68098. Thank you very much.
Thank you, Professor Zakaria. So there are some queries among the participants. So I would like to pick some questions. So could you please explain, there is one question from Nepal, from Mr. Tirtharaj Adhikari, how significant is the effect of extra cameral radiation in the field dosimetry and how should we overcome it?
Please, once again.
Let me word. I would like to share the questions because if I pronounce, it would be difficult to understand, you know. So I would like to share my screen, okay?
Yeah.
Okay. So there is one question, which is not this one. Could you please explain how significant? Are you seeing it?
Yes.
How significant is the extracameral radiation?
Extracameral radiation in the field of dosimetry.
How should we overcome it?
What is cameral radiation?
I don't know. This is the question which I have received.
What is cameral radiation?
Let's go to the another question. So maybe you will correct it and send me back again. What are the relations between lateral charge particle equilibrium range in the medium, RLCPE, and the detector size?
Yes, I have given a formula. This is the minimum field is 2 times RCP plus D. That means when you have detectors, maybe 0.5 centimeter diameter, and you have selected a energy maybe 15 MeV, then 2 centimeter, and the field must be 2.5 centimeter larger than that. So there is a relation. You can select, you can calculate it.
Okay, thank you. There is another question about photon beam. For energy response, can we use the same relation what we used to with photon and electron beam, which is already explained in TRS 398? So is it possible to use the same relation?
Actually, in the small field protocol, there is no electron dosimetry, but there is a photon dosimetry, and the relation is same, yeah. And
it's a continuation of that question. Can we use cobalt-60 as a reference beam?
Yes, yes. In both protocols, we use the cobalt beam as a reference beam.
What are the quality of parameters of the photon beam? R50 for the electron. Electron beam is already not R50.
What is the quality parameter for photon beam? I do not know exactly what is photon beam. The quality control is defined. Maybe I will see the literature.
And there is another question. Can we position the ionization chamber? Why should we position the ionization chamber in the horizontal direction, whether the solid detector is particle?
Because actually in a small field, you should find the position of the effective point of measurement. Yeah. Okay. And also to eliminate some disturbance during the measurement.
Okay. And can you comment the effect to source SSD, field size, energy, and detector type of relative output factor measurement, especially in small photon beam, and the effect of these as compared to the Monte Carlo simulation? Can we see it?
Can we comment the effective source to surface distance, field
size?
Yeah. Actually, this is for the standard dosimetry when you have other fields, there is a correction factor. You use this correction factor.
So let me check another other questions if there is any. Let me try. Can we measure relative output factor using larger SSD, making small fields larger, perhaps even at the gantry 90 degrees?
What do you mean? Actually, the larger SSD. Why should you need the larger SSD?
There is a question. Can we measure relative output factor using larger SSD, making the small field size? Means we increase the SSD and the field size, field larger, and we increase the field size, perhaps even at the gantry 90 degrees.
Yeah, I do not think any problem. It's possible to do that because it is actually the readings ratio and the correction factor. So it's possible. No difference.
So what is your recommendation on high energy beam or low energy beam for IMRT treatment? What is
actually, when you for the small field dosimetry, their advice, I see the modulation for the small, large energy is not so good, but the small energy modulation is good. So when you use the collimators, multi-leaf collimators, then the modulation is so bad. Therefore, for a small field, for high energy is not very suitable.
Okay. So there is one more question. How the centers which do not have MC simulation can determine the IAEA correction factor?
Yes, the both protocols, they have enough small correction factor, and yeah, you can use it. I have shown you actually how to determine, how to find the factors and put it in the dosimetry.
So let me add one more question.
Yeah.
If there is another. For the treatment of deep-seated tumor in the lungs, do you recommend beam less than 10 MB or more than 10 MB? What is your recommendation for the treatment of deep-seated tumor in the lung?
Yes.
What do you recommend? What is your recommendation? Whether we should use 10 MB or more than 10 MB?
Actually, in treatment planning, you have more other energies. You can, in this case, I think you take actually larger energy than 10 MeV.
I don't know about the time. Rajani, could you please let me know? Are we within a time? Then I take.
Only. We have 5 minutes only.
Okay, 5 minutes only. Okay, I'll take one more question. The last one with larger SSD. Can you see here? Because of the one, there is another message that the questions jump out. You know, that's a
yes. Many questions with larger SSD.
You can see the questions in your chat box also.
Yeah.
Here for you. There is one question with larger SSD, hence larger field size. Can I use the larger chamber with standard field size protocol instead of small field protocol? There is a question from Michael Lee. So it's in the chat box. If you have a problem to catch my voice, so you can see through your chat box.
Output factor collimator on gamma.
Not this one. With larger SSD, please kindly go a little bit.
Let me repronounce the question. It is with larger SSD, hence larger field size. Can I then use larger chamber with a standard field size protocol instead of small field protocol?
Yes, in larger field, you can, in standard dosimetry, you can use the large chamber. Yes, you can do that.
There is a last question. We can take this last question only as we have a time limitation. So it is output factor collimation on gamma knife. Can we put button collimator in PHSP file or must be in water phantom?
Please show me this question here.
The last one.
It's already there. So you can see it from your chat box.
In chat box?
Yeah. It will be easy for you to.
The last question. Oh, yes. Output factor collimation on gamma knife. Can we put bottom collimator in PS file or must be in water phantom? I have no idea.
Okay, then no, you can send the answer later on. So no problem. If anyone has any question regarding small field dosimetry and protocols, could you please write or directly email to Professor Zakaria?
Yeah. I can give some example because the gamma knife, they have special arrangement, and this is actually very new. I do not know which arrangement they have. So I should read little bit and then I can give the answer. No problem.
Okay, thank you, Professor. Then now I would like to hand over the floor back to Jean and our President Arun Chogle to give them remarks. And I would like to thank AFOMP for this opportunity to be a part as a moderator. It's a thank you very much. And I would like to thank on behalf of the Nepalese Association of Medical Physicists. So hopefully we'll do again and again. Thank you very much.
Thank you very much, Dr. Adhikari. Nice. Yeah.
Jin, are you taking over? Jin Sians? Okay, I think he is not available, maybe busy with something else. So let me thank Professor Ghulam Abu Zakaria for covering the topic very nicely and comparing both the German protocol with the IAEA protocol and answering the questions very nicely. Also at the same time, let me thank Dr. Kanchan Adhikari for nicely conducting this webinar. Thanks to the chair of the ETC Education Training Committee, Shian Jin, who is coordinating all this webinar. Thanks to Chai Hong for the PRC chair for arranging for your CME CP certification. Also thanks to Rajni Verma for all the technical support and the mobilization of the participant. And not the least, very important is participant, and almost more than 130 participants participated into this very good webinar. And as I talked about, due to this COVID, though we are not able to have in-person or physical meeting, education cannot wait or cannot stop. And therefore, we have started all these webinars. Every month we are doing the webinars. If there is a demand of more, we can do, but we thought that the dose of this webinar should not be too much because IOMP and other organizations are also doing the webinar. Your suggestion for interested topics are highly appreciated. We are planning the webinar till December. We have already planned. It is available on the website, also AFOMP website. And also we are now going to plan from January to June, coming 6 months, 2021. So please give us your feedback about the topics and the importance, what you need really, because at the end of the day, it is the interest of the participant, what they need to learn or what information they want to have. So your feedback will be highly appreciated. Also, I take this opportunity because Jin Xians was to show the slide, and invite you for the AOCMP 2020 is going to be held in Phuket in Thailand. And it's a joint meeting of AFOMP, CFOM, and also JSMP with the Thailand Medical Physics Association during the 3 to 5 December. Looking to the present situation, we have made this conference a hybrid conference. That means virtually also you can join to the conference, and also in person or physical if the situation is permitted. And I was talking with the organizers. They are hopeful by October, the Thailand, they will have the international flight starting and everything. And for the participation of the participant online virtually, the registration fee is almost 40% of the regular registration fee, which is on the website of the AOCMP 2020, also will be made available on their AFOMP website. So you are encouraged to register for this conference in person. If you can do that. If not, virtually join it. The scientific program is a very, very rich scientific program. We have made virtual presentation as well as in-person presentation. So take the benefit of this annual AFOMP and CFOM, JSMP, Thailand Medical Physics Association joint meeting to get benefited with this thing. So with this appeal, and appeal of again, your feedback is very, very important. I hand over the floor to Rajini Verma to conclude, and also again remind you, the participant who need the certificate, CPD certificate, as you know, 2 CPD points will be awarded for the participant. Please give your exact name and the country for this thing, what link has been provided. With this thing, I hand over to Rajini Verma.
Thank you, sir. Thank you very much to whole webinar team, especially Professor Zakaria and Professor Kanchan Adhikari for such an incredible talk and management of the discussion. So today's presentation was very important as we all are moving towards confined field therapies. So at last, I want to thank all the participants for such an active participation. And we all are looking forward to see you on 1st of October with another interesting scientific feast. So thank you once again, all of you.
Stay safe. Stay
Thank you. Thank you,
stay
the
safe, stay
AFOMP team. Thank you. Thank you, Dr. Chogle. Thank you, Dr.
Bye-bye.
Adhikari and Dr. Verma. Thank you. Goodbye.
Goodbye.